Okay, good afternoon. In the last lecture, we had been looking at a discontinuous conduction when fully controlled converter, single phase fully controlled converter is feeding a separately excited DC motor drive. So this is the fully controlled converter. Let me draw the circuit diagram again so that we are clear about what we are talking. So these are the four devices which are making up for the single phase fully controlled bridge converter. And here is the separately excited DC motor drive. And here is the field which is carrying a constant current of IF. And the single phase supply is here. So this is the single phase supply. And we are looking at A and B as the terminals of the single phase supply, which is having Vm sine omega t as its expression, the voltage expression. And these are the devices T1, T4, T3, and T2. Now, we had seen that in motoring operation, basically we are going to have VA minus IARA equal to EB. And we are going to have VA divided by K5 minus TE RA divided by K5 whole square. That is going to be omega. And we said that basically this VA, the expression for VA varies. So this varies as per alpha and also based on continuous or discontinuous conduction. Okay. Now, if we want to implement regenerative braking for this particular motor drive, if I want to implement regenerative braking, can I do it using a single phase fully controlled converter? That is the question I have to ask myself. So if we are talking about continuous conduction, we said that VA equal to 2 Vm by pi cos alpha. If I am talking about continuous conduction, this expression is valid. So this is going to be the armature voltage, terminal voltage that is being applied. And as per this expression, we can say if alpha is lying below 90, in that case, VA is positive. What I mean is the average value. We are not looking at the instantaneous value. We are looking at the average value. VA average value is going to be positive. Rather, if alpha is greater than 90 degrees, then VA is going to be negative. The average value is going to be negative. One more thing I want all of you to understand is that if I am having T3 and T2 conducting previously, and I'm trying to fire the converter for the positive during the positive half cycle at a value of alpha less than 90. When alpha is less than 90, let us again look at the waveform. So this is going to be the kind of sinusoidal supply I'm having. This is omega t. So if I am looking at something as alpha here, and let us say the back EMF is somewhere here. The back EMF is somewhere here. So we are going to have actually, when I am firing T1 and T4 here, and if I assume T3 and T2 are already conducting, then this point B is going to be connected here. So this point B comes into existence at this point, at here, at this junction. So VAB, what happens to be your supply voltage itself, that will have positive here and negative here, due to which T1 will be forward biased. The same will be the case as far as T4 is concerned, this will be positive and this will be negative because this is a short circuit. You are going to have this as positive because this is a short circuit and this is going to start conducting. So if T1 and T4 start conducting at this point when I am firing it at alpha, then what is going to happen is, now if T1 becomes a short circuit, I should show it as though it is a short circuit like this. And if T4 is a short circuit, this becomes a short circuit like this. So whatever logic we applied for turning on T1 and T4, the same logic we should be able to apply for turning off T3 and T2. So now T1 has started conducting, so that becomes a short circuit. T4 starts conducting, that becomes a short circuit. So this point B now comes into existence here also. This is going to be B. And this point is A anyway. So VAB, if you look at it, VAB is positive, which means that is going to reverse bias T2. So T2 and T3 behave as a short circuit before firing T1 and T4 at omega t equal to alpha. Okay. So because they are short circuit, now we are going to see that T1 now is applied with a voltage VAB, which is the same as the supply voltage. And because it is positive half cycle, T1 will be forward biased. So T1 is going to be forward biased. So now that T1 is forward biased, T4 behaves the same way as T1. So both T1 and T4 start conducting at omega t equal to alpha. So now T1 and T4 behave like short circuits. Now, applying the same logic as in step 1, we can see that T2 and T3 get VAB across them with their cathodes being more positive than the anodes. So they are reverse biased. So they go off. So at alpha, when you fire T3, T1 and T4, you would see that because these become like short circuits, this point B, which is coming here, that point B comes up here. And because this is becoming B and this point is A, so T2 is going to get VAB. And VAB now, if you look at it, that is the positive voltage. So the cathode becomes more positive than the anode. So T2 goes off. The same way T3 also, you can write the logic and T3 will also go off. And this VAB becoming positive will be valid only until alpha equal to pi. So if I have a firing angle greater than 180 degrees, the commutation of T3 and T2 will fail. So we can have the commutation. So the commutation or turning off of T2 and T3 will be successful only if alpha is less than or equal to 180 degrees. So the maximum alpha feasible is 180 degrees or pi radians. You can't have more than that. Okay. So if you look at this expression, when we talked about VA equal to 2Vm by pi cos alpha, when alpha is less than 90, we said that VA is positive, and this is going to result in motoring operation. And if I am going to have alpha greater than 90, VA will be negative. But we have to check whether regeneration is possible. We have to check this. We have still not, come to a conclusion. We have to check whether it will be possible for us to implement regenerative braking during this particular situation when alpha is greater than 90. But all the same, we cannot have alpha greater than. So alpha max can be only 180 degrees, nothing more than that. So this is between 0 and 90, and this is going to be between 90 to 180. So this is the range in which the machine might work in regenerative braking operation, which we have to check. Again, all this expression is valid only if we are talking about continuous conduction. If we are talking about discontinuous conduction, first of all, even this expression is not valid. 2Vm by pi cos alpha itself is not valid. So you may not be able to really come to these conclusions if it is discontinuous conduction. So now let us try to take a look at regenerative braking. So whether we would be able to implement regenerative braking or not, let us try to see. So we already said that if we are going to have the DC motor drive here, and normally we are going to have the converter connected here. So let me again show the four devices, all four devices of the converter that is connected here. And we had been having the terminal voltage of the converter with plus here and minus here when alpha was less than 90 degrees. Okay, so this what we are applying here is Vm sin omega t. If alpha is less than 90, in that case, we had plus here and minus here. And at that time, we also had plus here and minus here, which was the back EMF, and we were having the field having a current in a particular direction like this. So when we are talking about motoring, we will have generally VA greater than EB. This is going to be the motoring operation. And we are going to have the current flowing into the motor. So the current is flowing into the motor. So this is going to be the direction of IA. And we are also looking at alpha less than 90 degrees. So between 0 and 90 degrees, alpha will be existing. So 2 Vm by pi cos alpha is going to be positive. So this is going to be a positive value. Now, if we are looking at regeneration, so regeneration, we said that it can probably be implemented if 2 Vm by pi cos alpha becomes negative. So if it becomes negative, that means we are going to have these signs changing. So we are going to have essentially, let me complete this circuit because this got erased. So this is going to be the circuit. And VA, if I look at it this way, now this is going to be positive and this is going to be negative. So the armature terminal voltage is going to change. It's going to reverse. So VA reverses its polarity on an average basis. This is going to be reversing its polarity on an average basis. So once this becomes negative, please note that all these devices can carry current only in this direction. They cannot carry current in opposite direction. So I cannot expect the current to reverse. So armature current cannot reverse. So IA cannot reverse. So IA has to flow in the same direction. It has to flow in the same direction. Whereas VA has reversed its polarity. So is there a way that we would be able to feed back VA times IA? Can this be fed back to single phase means? Can this be fed back to single phase means? Only then we can call it regeneration. So if let us say either I reverse the direction of field current, or I reverse if I say that this is A1 and this is A2. Now what I'm going to do is to reverse this connection itself. I want to make this as A2 and this as A1. So if I try to make this as A2 and this as A1. So if I am able to make that, then automatically the back EMF would also reverse its polarity. It will have plus here and minus here. So if I am going to make this as plus and this as minus, in that case, so I'll have to remove this. This was the original sign. Now this is the sign that is now the case with the reversal of either armature or field. Armature terminals have been reversed, the connection has been reversed, or the field current has been reversed. So now if alpha is adjusted such that VA average value, that is 2 Vm by pi cos alpha, is less than, it is going to be less than EB magnitude. If I do this, then automatically the current is going to flow from EB into the devices and the power will be fed back to the AC mains. So I can implement regeneration by either reversing field current or reversing the armature terminal. And simultaneously, I have to adjust alpha. Alpha, of course, has to be greater than 90 such that this condition is satisfied. That is 2 Vm by pi cos alpha magnitude is less than EB. In that case, it can work, in regenerative braking mode. Let us try to take some value. For example, let us say I am working at alpha equal to 30 degrees. Okay, maybe the input value is something like 230 volts, 50 hertz supply. So this is going to be Vm sine omega t. So this is going to be 230 multiplied by root 2. So 325 sine omega t. That is going to be my input. And this is the firing angle. And approximately what we are going to have as the voltage will be 230 multiplied by 0.9, which is actually the output for a diode rectifier, single phase diode rectifier. That has to be multiplied by cos 30, which is 0.866. So the voltage what we get will be approximately 180 volts. So what we get as 2 Vm by pi cos 30 will be approximately 180 volts. So if by chance the machine is having 1 ohm armature resistance, and if we are talking about a current of 10 ampere, then we are going to have the back EMF to be 180 minus 10 multiplied by 1. So this is going to be 170 volts. So this is going to be very clearly motoring operation. We are having EB less than VA, and whatever is the power that is being developed is 170 multiplied by 10, which is 1.7 kilowatt. So I'm calculating EB multiplied by IA. This is going to be the power that is developed by the DC motor. Okay. Now this is clearly going to be motoring operation. So if I want regeneration, so let me see what can be the case for regeneration. So during regeneration, let us say armature terminals are now instantaneously reversed. Okay, so if armature terminals are reversed, then I am going to have 170 volts. EB will be still 170 volts, but it is going to be reversed. The voltage is going to be reversed. And what I want is VA magnitude should be less than 170 volts. Only then IA will flow from the machine to the mains. Otherwise, it's not going to work like, a generator. So if this has to be less than 170 volts, obviously we got 2 Vm by pi cos 30 as 180 volts. So if I try to put 2 Vm by pi cos of 180 minus 30, then also I will be getting this voltage to be 180 volts, but this will be minus 180. This is what I'll be getting as the voltage. So if I just reverse the armature terminal and I also abruptly change the firing angle from alpha to 180 minus alpha, that's not going to do the job because VA is not going to be smaller than EB. So if I want if VA has to be smaller than EB, so if I want this to be achieved, then what I need to do is maybe I will require 160 volts or something. So I should say 2 Vm by pi cos alpha equal to 160 volts with the negative sign. So if this is possible, then I would be, my machine will be actually working in regenerative braking case. So what I need to do is 230 multiplied by 0.9, that is what is 2 Vm by pi, that is about 207 volts. So I should say now 207 multiplied by cos alpha equal to minus 160 volts. So I should be able to say cos inverse of 160 minus 160 divided by 207. That is what I'll have to find out what it is. So that is going to be about 140 degrees. So I'm going to have this firing angle now shifted from 30 degree to 140 degrees. So if I do that, then I may be able to achieve regenerative braking. So what will happen is the kinetic energy that is stored in the rotating parts here, it is already rotating with omega. So at a speed omega. So this is going to generate back EMF further and further because there is kinetic energy and there is field current. So this plus is going to be greater than this particular positive because this was only 160 volts, whereas this was 170 volts. So the current will flow in the same direction, but the power is now flowing back to the single phase main. So you are going to have the current flowing like this, and then it is going to return the power to the single phase mains. Now, because it is returning the power, the speed will decrease. Once the speed decreases, the back EMF originally was 170 volts. So EB will decrease as more and more power is fed back. More and more power is fed back to the mains. So you are going to have EB decreasing because the speed is decreasing. Okay, speed will decrease and EB will also decrease. Both will decrease. So now EB might become 150 volts from 170. So we have to adjust alpha further such that we get lower and lower values of voltage. So from alpha equal to 140, we may shift to alpha equal to 120. Then eventually we may shift it to alpha equal to 110 as EB decreases from 150 to 140 to 130 and so on. So it will keep on decreasing further and further, and alpha you have to go towards 90 degrees. And once you go to alpha equal to 90 degrees, you are going to have 2 Vm by pi cos alpha equal to 0. So at that point, slowly the speed would also have decreased quite a bit. And you might see that there is not much energy left over, kinetic energy left over in the rotating parts. So the regenerative braking can bring it down to literally zero speed. Until zero speed, regenerating braking would have taken place and it would have converted the kinetic energy stored in the rotating parts into electricity, and then it would have fed it back to the single phase mains. So this is how the regenerative braking can be implemented in the case of the single phase fully controlled converter. So if you actually look at the waveform corresponding to regenerative braking, this is the power supply voltage. Okay, and this is omega t. So let me again draw the rectified voltage also. Now what you need to remember is EB has reversed its sign. So I should show as though EB is in this particular sign. So this is going to be EB. Okay. Now we are looking at an alpha which is greater than 90. So let me show this alpha which is greater than 90, and this is going to be pi plus alpha, where we are going to fire T2 and T3, whereas we are going to fire T1 and T2 here. So at this juncture, if you try to look at it, until from this point until this point, you are having EB is smaller as compared to VA. So we are going to have the current increasing until here. And after that, the current is going to fall. And it will fall until this point. If you try to allow it to fall until this point. But at this point, you are going to fire T2 and T3. So again, the current will increase and it will fall. So the same thing is going to happen repeatedly. So you are going to see that this is the kind of waveform for the armature current you get. So this is going to be the armature current waveform. And if you look at what is the terminal voltage, what you get as the armature voltage is this, and it will go on until here. So this entire negative portion is going to come up and only a small positive portion is going to come up. So if I try to look at what is the kind of integration that we need to make, you have to say from alpha to pi plus alpha to Vm sine omega t d omega t. And this is averaged over pi. This is going to be averaged over pi. So this comes out to be again 2Vm by pi cos alpha. When alpha is greater than 90, automatically you are going to get average value as negative because the negative portion is dominating over the positive portion. The positive portion is much smaller than the negative portion. That is the reason why you are going to get the overall value across the armature is going to be negative. Instantaneously, it will have positive and negative. There will be positive excursion as well as negative excursion of voltage. But on an average basis, you are going to see that it is mainly negative. The average value is negative. So regenerative braking is implemented by either reversing the field connection or by reversing the armature terminal connections, and also simultaneously making alpha greater than 90, the firing angle greater than 90. So this is the way generally the regenerative braking is going to be implemented. And that is the reason why we say that single phase full converter, single phase fully controlled converter. So this will be in a position to offer two quadrants of operation. So it will be able to provide motoring and regenerative braking, both. It will be able to offer both motoring and regenerative braking. And one thing what we have to realize is IA is not reversed, but EB is reversed. EB as well as VA average also. Both are reversed. So this is the way generally your regenerative braking operation works. So that is the reason why we say that fully controlled converter can give us two quadrants of operation. So this is a two quadrant converter. It will be able to provide me with motoring as well as regenerative braking. That's why we call it as a two quadrant converter. Okay. Now let us try to complete the speed torque characteristics what we had drawn earlier for single phase fully controlled converter. So let me first of all draw whatever I had drawn earlier. So this is going to be TE, or in one sense IA. Both of them are synonymous with each other. They are proportional to each other because we are keeping excitation as a constant. And this is going to be omega, or indirectly it is going to be EV as well. Okay, so this is the way it is going to be. And what we drew earlier was at alpha equal to 0, probably we are going to have it like this. Alpha equal to 15, 30, 45, 60, and so on. So this is going to be alpha equal to 0. This is going to be alpha equal to 15, alpha equal to 30, maybe alpha equal to 45, alpha equal to 60, and so on. So we are showing different speed torque characteristics, but all of them are only corresponding to continuous conduction. Now, when we are actually looking at the waveforms corresponding to single-phase fully controlled converter, we drew the back EMF much lower than the peak of the sinusoidal supply voltage. And we said that if I'm going to have an alpha, which is somewhat like this is alpha, we are going to have the current increasing and decreasing and increasing, decreasing, and so on. This is the way the armature current is going to be. Now, if we are decreasing the load demand further and further, this current is eventually going to become, discontinuous. So I may have the current somewhat like this, and correspondingly, I might see that the back EMF becomes much higher because the torque has become really small. So this is EB dash, and this is going to be IA dash. Whereas this is going to be EB original, and this is going to be the corresponding IA. This is going to be the corresponding IA. So once I throw off more and more load and I'm going more towards no load, at that point the back EMF is going to increase quite a bit. The maximum value of back EMF theoretically is that point where EB average value is equal to the peak of the sinusoidal voltage. So if EB is equal to VM, this is the condition where the devices may not turn on at all, because I'm not going to have them forward biased anytime. It's not going to get forward biased at all. So if EB equal to VM, at that point, you are not going to be able to make any device conduct, which means IA is going to be 0. And if IA is 0, TE will also be 0. So this is the ideal no load condition. So ideal no load condition is that condition under which I'm not going to see any current through the motor drive at all, which means none of the devices can get fired. So if none of the devices are getting fired, that means in all probability back EMF should be equal to VM. So I should be able to say K phi omega equal to VM under ideal no load condition. So which means omega no load speed will be Vm divided by K phi. This is going to be the kind of ideal no load that I'm going to see. This is the ideal no load speed which I will see for this motor drive. Now, if I say that I'm going to have something like a 210 volts DC motor, 207 volts DC motor. I'm specifically taking a value for some purpose. So this is a 207 volts DC motor. And let us say I want to make sure that my converter is able to feed 207 volts to my DC motor when it is working at alpha equal to 0 degree. So at alpha equal to 0 degree, the converter employed should be able to feed 207 volts to the DC motor. So if I am looking for the design of the converter, I should definitely have my converter feed at least 207 volts to my DC motor. when it is working at a firing angle of alpha equal to 0 degree, which means 2 Vm by pi cos 0 is going to be 207 volts. So from which I should be able to calculate what is Vm. So Vm for this particular case happens to be 207 divided by 0.9. So that comes out to be 230. So Vm, whatever, not Vm, Vrms happens to be 230 volts. So Vm will be 230 multiplied by root 2 volts. So if I try to calculate with this expression, I will get Vm to be 325 volts. So if I had connected a DC motor with the DC supply of 207 volts and I had connected it to my DC motor, then I would have gotten my speed torque characteristics in such a way that this can hit the speed axis and this will correspond to 207 volts. But when I am looking at a converter feeding this motor, so I am getting 207 volts with my converter being working at alpha equal to 0 degree. So I'm showing a converter as a black box and I'm going to feed it from the converter. And here is my single phase supply. So the single phase supply, what I have got here, this is going to have 325 volts as the peak. Only then I'll be able to get 207 volts at alpha equal to 0 degree. So I am looking at 325 volts as the peak. And if you look at what we derived as the no load speed, you are going to get the ideal no load speed to be 325 volts divided by K5. Whereas when I am feeding it with a normal DC supply, this is going to be 207 volts divided by K5. So if I try to look at what is the kind of value I am having here, if I try to get the speed is going to be 207 divided by K5. Whereas ideally I should have gotten, I have to extend this axis. And between 207 and 325, if you try to look at what is the kind of ratio we have. So let me calculate what is 325 divided by 325 divided by 207. So this is almost 1.57 times. So I should have actually my ideal no load speed will be, this is 1 time and 1.5 is somewhere here. So from here, I have to connect it to this. So I'm going to have from the ideal no load speed, slowly it will get connected to this continuous conduction case. So all this portion is corresponding to discontinuous conduction. This is going to be corresponding to discontinuous conduction. And what we have here, this is going to be 325 divided by K5. Whereas this is going to be 207 divided by K5. So for a converter fed separately excited DC motor, the ideal no load speed is going to be almost 1.57 or 1.6 times that of whatever is the ideal actual no load speed for a DC supply fed DC motor, battery fed DC motor. Now, if alpha equal to 15 or alpha equal to 30 or alpha equal to 45, for none of them, the ideal no load speed is going to be any different because wherever I am firing them, I will have the pulses going on for 180 degrees. So this is going to be spanning over 180 degrees, train of pulses. So if I am taking alpha equal to 45, I would have had from alpha equal to 45 to 225 degrees, I would have had the firing pulse continuously coming up. So within that interval, at least at some point, my device would turn on. if the back EMF had been less than Vm. So I am not going to really see any current at all for this case of alpha being less than 90 degrees, only if I'm going to have the back EMF equal to the peak of the supply voltage. So that is the reason why ideal no load speed is going to be still Vm by K5 for alpha lying between 0 to 90 degrees. So until 0 to 90, I will have to join all the characteristics from the same no load speed only. So I'm going to have all of them joining with the same no load speed point. So if I call this as alpha equal to 90, I'm going to still have this somewhat like this. This is how it is going to be. So I have to essentially draw it in such a manner that this is corresponding to alpha equal to 90. So from alpha equal to 0 to alpha equal to 90, the speed torque characteristics are going to be like this. And I should show as though these are all discontinuous conduction region. And only from here it is going to be continuous. So continuous conduction and discontinuous conduction boundary is shown here. Okay. Now, if I am trying to look at what happens when the boundary between discontinuous and continuous conduction, where it exactly occurs, if I want to know. See, what happens is, let us say I'm going to have my sinusoidal supply somewhat like this. And I'm going to have my alpha somewhere here. And pi plus alpha is somewhere here. And let us say the current is increasing from alpha. And it has reached the peak somewhere here. Maybe my back EMF is somewhere here. Let me show the back EMF somewhat like this. So this is the back EMF I'm showing. So this is the point where the intersection is happening. So the current might just touch 0 at this point. And from here, it might again rise and then fall like this. So this is going to be I. So the boundary between continuous and discontinuous conduction occurs when I'm going to have beta exactly lying at the point of pi plus alpha. So when pi plus alpha equal to beta, at that point, boundary between continuous and discontinuous conduction happens. So, if you may recall, we had written the expression for IA of omega t as Vm divided by Z sine of omega t minus phi minus EB by RA divided plus K1 multiplied by e power minus t by tau A. This is what we wrote as the expression for the current. Now, if I say K1 can be solved for by putting IA of alpha equal to 0. So if I do this, if IA of alpha equal to 0, then I should be able to write this as IA of alpha equal to 0, which will actually correspond to Vm divided by Z sine of alpha minus phi minus EB by RA plus K1 multiplied by e power minus omega t, which is alpha divided by omega tau a. So this is what is 0, from which we can solve for what is K1. So K1 will come out to be EB divided by RA minus PM by Z sine of alpha minus phi. The whole thing has to be multiplied by e power alpha divided by omega tau a. So this is K1. Now substituting this K1 here in this equation, we should be able to get a closed form expression for IA of omega t. So IA of omega t can be obtained with this substitution. Now, once you obtain this, particular expression, now you can say IA of beta, which will be equal to IA of pi plus alpha equal to 0. So once you obtain the complete expression for IA of omega t, now you put omega t equal to pi plus alpha and write this down. So that will probably come out to be Vm divided by Z. That is going to be Vm divided by Z sine of pi plus alpha minus phi and minus EB by RA. These things will not change. Now for K1, I'm going to substitute e power alpha divided by omega tau A multiplied by EB by RA minus Vm divided by Z sine of alpha minus phi. So this is the entire K1. And this has to be multiplied by e power minus t by tau a. So t I can write as omega t by omega tau a, and omega t happens to be pi plus alpha divided by omega tau a. Now in this expression, I should be able to obtain what is EB. If I equate this to 0, I should be able to get an expression for EB. Once I get an expression for EB, so obtain EB from the above expression. That is IA of pi plus alpha equal to 0. So once you obtain EB, you can say omega, which is the boundary between the continuous and discontinuous conduction, the mechanical speed, which is the boundary between continuous and discontinuous conduction, which we call as the critical speed. So we call this as critical speed. So this critical speed omega mc can be obtained after getting the expression for EB and dividing that by K5. So this will be able to give us what is the critical speed. So please try to derive this expression and cross verify whether it is matching with whatever is given in the book by G.K. Dubey or anybody else, because there are many books which give this expression clearly. So the critical speed is for a given alpha. This is going to be for a given alpha and for a given DC motor. So this, if you are given a particular value of alpha and if you are given the parameters of a DC motor, you would be able to get exactly what is the critical speed, what is the boundary between continuous and discontinuous conduction. If the speed is above this critical speed, you are going to have discontinuous conduction. And if the speed is below this particular speed, you are going to have continuous conduction. So you would be able to get exactly what is the critical speed. Now, we said that the boundary between continuous and discontinuous conduction is given, shown by this black line, whatever black line I had shown. So this is going to be the boundary between continuous and discontinuous conduction. And the ideal no-load speed is in general Vm by K5 for any alpha which is lying between 0 degree and 90 degree. But if you are going to have alpha greater than 90, so if alpha is greater than 90 degree, then what happens? So you are going to probably fire the device either here. Let me again draw the waveform, that is probably simpler. So if I'm going to have my sinusoidal supply like this, and I'm going to fire probably at an alpha which is greater than 90. So these are all alpha greater than 90. So if it so happens that the back EMF is exactly equal to Vm sine alpha. So this is, if I call this as alpha 1, so here I'm going to have EB equal to Vm sine alpha 1. And similarly, if I call this as alpha 2, I'm going to have this as EB equal to Vm sine alpha 2. So at alpha 1 or alpha 2, when I want to fire my devices, the converter devices, and if it so happens that the back EMF is exactly equal to Vm sine alpha 1 in the first case, or EB dash equal to Vm sine alpha 2 in the second case, you are not going to have any of the devices getting forward biased. So if alpha is greater than 90, and if Vm, if the back EMF, so if EB equal to Vm sine alpha, none of the devices will be forward biased, and hence they will not conduct. So under such a situation, we are going to have literally IA equal to 0. So I should say ideal no load speed, mechanical no load speed. So let me not confuse between sine omega t and this particular omega. Omega m is actually the mechanical speed of the motor, whereas this omega, whatever we had written, these omegas are all corresponding to 50 hertz, that is 2 pi f, which is about 340. So the two are different from each other. So this, whatever we wrote as ideal no load speed, so I should say omega m ideal no load speed is Vm divided by K5 for alpha less than 90 degrees. Whereas the same ideal no load speed will turn out to be Vm sine alpha by K5 when alpha is greater than 90 degrees. When alpha is greater than 90 degrees, so alpha lies between 90 and 180. When it is lying between 90 and 180, because the maximum alpha is only 180. So if I try to draw the actual characteristics corresponding to alpha equal to say 120. So for alpha equal to 120, I should again have the characteristics lying in fourth quadrant, because we are looking at back EMF becoming negative. The current is still remaining positive. So IA is positive, VA and EB are reversed. So we are going to have regenerative braking in this particular case happening in fourth quadrant, not in second quadrant. So if I draw one more characteristics corresponding to 120 degrees, and I'm going to have alpha equal to 150 degrees. So Vm sine 120 is going to be 0.866 times Vm. So we will have 0.866. So this is Vm. So 0.866 might lie somewhere here. So I have to actually join from here, and it should come into this particular characteristics. And similarly, if I draw for alpha equal to 150, again, I should draw it like this. And for 150, sine 150, it will be 50% of whatever was the original speed. So this is going to be Vm sine 150 degrees by K5. Whereas this particular point, what I have got, right? So this point is going to be what I have written here. This is going to be Vm sine 120 degrees divided by K5. So I have to join this particular point, sine 150 point, to this alpha equal to 150 degrees characteristic. So these are going to be the kind of characteristics we obtain for the two quadrant operation of the DC separately excited motor when we feed it with the single phase fully controlled converter. So this kind of takes us to the conclusion of single phase fully controlled converter. Just to summarize what we had seen in single phase fully controlled converter fed DC motor drive. So we had mainly looked at, first of all, we looked at continuous and discontinuous conduction, how the motor behaves. And especially in discontinuous conduction, we looked at two cases, alpha greater than gamma and alpha less than gamma. And even in alpha less than gamma, we looked at where beta is going to be less than pi plus alpha and beta is going to be greater than pi plus alpha. Two cases we saw. Then we derived the expressions. So derivation of IA of omega t from the differential equation. And we also derived the speed torque expression. Then we drew the speed torque characteristics. Then after that, we also looked at both motoring and regenerating operation, how these things can be achieved by changing the connection of the armature or changing the field current direction. Then we also derived the ideal no load speed values for alpha ranging from 0 to 180 degrees completely. Okay. So in the next class, we will try to work out a few problems on single phase fully controlled rectifier so that we understand the working of the entire drive for various ranges of speed and torque. We'll try to look at a discontinuous conduction case as well.